In mathematics, connections are hugely important, and today we will be talking about the connections between mystic rose patterns, triangle numbers, and the Handshakes problem. This will show you how to engage your learners to be fascinated by mathematics.
Today we're going to talk about triangle numbers, and there's lots of patterns here. There's patterns of shapes, we call those perhaps geometrical patterns, and there's patterns of numbers. So, well, Caroline, what do you notice about these patterns?
Let me see. Well, I can see why they're called triangle numbers. I see that, well, there's the dot. That's just one dot. So that one I'm not sure about, but the others are very clearly triangle numbers. And I can see that if they're static, we're not moving them. Each one has got a, well, let me do it the same way around and that way around. Each one has a diagonal line added. But also something else that I feel like it's as though it could be a column that's added, or a row, that a column to the left, or a row at the bottom has been added. But that's, they're no longer static, but they could be built up doing it that way as well. I see that.
Caroline, you mentioned number one. Well, quite often in mathematics, something arises which is a simple case of a general pattern, and one is the first triangle number. You're not seeing, as it were, a triangle of dots there, but it is consistent with what you've just described. The way the pattern is formed by putting an extra row or column or diagonal, whichever way you like to think about it, the pattern is growing, and it's starting with one. And so one is a quite simple triangle, but it is a special case. So if you shrink the triangle numbers, if you think of shrinking them down by taking off a row, then you get back to one.
Right. Okay. So one is valid to have in that sequence.
Indeed.
So that's nice. That's comforting to know. So what else have we got? I can see, yes, I see your numbers. I'm looking at this. So T1 to T6, I take that to be a triangle 1 is a single dot. Triangle 2 is 3 dots. And then I've got the numbers below where we've got 1, 1 plus 2, 1 plus 2 plus 3. Well, I can see that very clearly. That is how many diagonal dots there are. So in the diagonal, wait a minute, let's follow the same that way. One, there's just that's one, yeah. 1 plus 2, there's a dot, and then there's a diagonal with 2, and it just goes
Caroline, on. Can I just say, I agree with what you're saying. Of course it's right, but it is easier if you start from the top and go down. So if you think of, oh yes, I wanted to say also that these, we want to give them a name. So we're calling them T1 for the first one, T2 for the second one, T3 for the third one, and so on. The 100th one is called T100, and that thing, we write the number down as what we call a subscript. So the next one isn't shown.
Hold on, Toni. I'm not ready to go there. You said something, and I was adding the diagonals on, but now you said it's easier if you go down. So you're adding a row on. You're saying it's easier.
I think that's easier.
Upwards. So it's going upwards, and you'll keep adding a row on at the bottom.
No, start at the top and go 1, 1 plus 2, 1 plus 2 plus 3, and then for T4 it's 1 plus 2 plus 3 plus 4. Look at the rows and just go down, and you'll find.
Okay, so for each triangle,
you can do anything, Caroline. It's fine to do what you were doing.
Because I've always looked at the because we've always had them in the past. We've had them laying on the hypotenuse on the longest edge. So you've turned them around on me. So but you can do it just as that's what I meant about the rows and the columns anyway, that you can quite happily add a row at the bottom of if it's sitting this way, you can do it whichever way it's sitting.
That's a nice thing about it. I mean, there's different ways of looking at it, different ways of visualizing the triangle, if you like. But my point was that what you were doing was, what you were saying was absolutely right. But it is easier whichever way round the triangle is, to start at the top and work your way down, because you've got 1 at the top, then underneath it you've got 2, then underneath it you've got 3. And when we come to T6, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is why we
going down. Yeah, I can see it. Yeah. Mm-hmm. Okay.
Now, then there's a question, and this, you wouldn't really want to draw the dots for this, would you? For T100.
No, I don't think I want to draw the dots for T100. Thank you very much. No.
So let's approach this a different way. Let's try and do it an easier way. So this is a little bit of a diversion. This is about, this is about clever Carl. And the story is, it's about Gauss, who was a famous mathematician, but of course not famous when he was a child.
Was it? So his name was Carl Gauss, was it?
Yes, and he was Carl Friedrich Gauss. But he, as a small boy, his teacher gave the whole class to add 1 plus 2 plus 3 plus 4 up to 100, which is the question we just asked. And the teacher thought he'd given this question, the children would add these numbers. It would take them quite a long time, and the teacher could just sit back and relax, and it would be good practice in addition for the children. Well, the teacher got a surprise, because in about 2 minutes or less, Carl put his hand up and said, "Sir, I've done it." And his teacher was hardly could believe it. And so he asked him what answer he got, and the boy told him the answer, and then the teacher knew that it was right. And so this is what he had done. Can you see here? Adding the numbers 1 plus 2 plus 3 plus 4, and going on up to 99, and then adding 100, going from left to right, you can imagine that. And then what Carl imagined, which was extremely clever, was to flip them round and start, instead of starting at 1, to start at 100. And instead of counting up, to count down. So he counted 100 plus 99 plus 98 and so on. Well, he didn't add them. He just wrote them in that order.
Yeah,
he just wrote them in that order.
In the reverse order, he wrote them in the going 1 up to 100 going up, and then starting at 100 going down to 1. And it's what an insight. What an incredible insight that was.
So what do you see about that pattern?
Well, what I see is, and it makes total sense seeing it, is that 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. It's just the thought of actually having done that, having reversed the numbers. If you do that with any number, presumably, you end up, if you add those two numbers together, you will always end up with the same number.
Yes, if yours, it actually works for other. These are called arithmetic sequences. It works for any of them, because if you take the same sequence and reverse it, and you go up with 1 when you write the sequence down one way, and then you go down when you write the sequence the other way, the sum of the terms that you've put underneath each other, as it were, will always be the same.
Fantastic.
Isn't it lovely? Yes.
Absolutely.
And so what's this? This gives us the answer to the question we just asked. It gives us the answer beautifully.
100 times 101 is super easy to work out. That's 10,100. And then half that, bingo, 5,050. It's I love it. I really love it.
Well, when he grew up, he became this young man, Carl Friedrich Gauss, as you can see on the stamp. He was a famous mathematician when he was still quite young. And there is a picture of him, not as a boy on this stamp, but as a young man. And here's a picture of him on a banknote as quite an old man. This was Carl Friedrich Gauss, born in 1777, died in 1855. And he was what people have described as a polymath. That actually didn't have anything to do with mathematics. It was more a description, math being used there in the sense of what you know and understand. In his time, in the the late 18th century and the early 19th century, a person, a scholar, could know more or less all that was worth knowing. Well, not so much all that was worth knowing as what was known was so limited that one person could actually learn it all in his lifetime or her lifetime. Nowadays, there's so much out there that's been discovered since Gauss that it would be absolutely impossible. And what's even worse in the sense is that there are new discoveries being made every day faster than anybody could, in mathematics even, if you just stick to one subject, faster than anybody could possibly study them and learn them. So yes, there's been an explosion of knowledge, really.
And yeah, but having said that, Gauss was part of the explosion because he didn't just learn everything there was to know, he developed it, he made new discoveries, and which is, this is beautiful. Now, if people are saying to themselves, Gauss, that sounds familiar. I've heard of Gaussian distribution. Would that be?
Oh, yes. I mean,
Gauss?
he worked in very, very many different branches of mathematics. And he actually, as you so rightly said, Caroline, he laid the foundations for further work in all sorts of fields of mathematics. So you're right, he was part of that explosion because he had so many good ideas that people later were able to expand on. And this was one of his ideas. It's called the Eureka Theorem.
Oh, let's put that one on. Go on.
And what his theorem was that every number, whole number we're talking about, integer, can be written as the sum of 1, 2, or 3 triangular numbers, right? So you don't need 4, you can do it. Of course, the triangle numbers themselves are just one triangle number. And then there are some numbers that can be written as 2 triangle numbers, and all the rest can be written as 3 triangle numbers. Isn't that beautiful? Another picture. Yeah. What do you notice in this picture?
Well, I see 2 number triangles, but they're put together. They're not put together the way I'd expect them to be put together, because normally when I split, I can see a rectangle, but normally when I split it in half, I literally go from one vertex to another. So I'm literally splitting in half. This is 2 halves, but they're offset. So
they're actually the same triangle number. And it's rotated, and we've shown one in green and one in purple, so we can see that it's 2 triangle numbers. So what is the triangle number that is pictured there?
So that is 1, 3, 6, 10. That's 15. That's the triangle number 15, but it's 2 times. So there are actually 30 dots there. There are 2 15 triangles, so it's, and there's 2 times that amount of dots, so there's 30 dots.
Well, it's T5, isn't it? Because it's 1 plus 2 plus 3 plus 4 plus 5.
We have a nomenclature. We have a way of referring to these triangle numbers, and yes, if I use it correctly, I can get to that really easily, because all I have to do is count one edge, so I can count 5 dots, so therefore it's a T5.
That's
okay.
Right. And what you said, Caroline, what you said was right. You've got a rectangle, and there are 15 dots in the green triangle number, and there are 15 dots in the purple one, which makes 30 dots altogether. But if you see the rectangle is a 5 by 6 rectangle. So what that tells us, that 2 T5 triangle numbers make a rectangle. And as you told us, that was 2 T5 triangle numbers is 5 times 6 is 30 dots. So that gives us T5 equals 15. And it's written there. And that's what Caroline just talked about.
Now wait, you said T1000, what, to work out T1000. So to work out T1000, all we have to do is say T2 times T1000 equals 1000 times 1001, which equal to whatever that is, which is, I have to write down the ones so I don't get the wrong amount of ones. And then that's how you, that's it. That's how you know.
Isn't that lovely? Well, we were talking about
half of that. T1000 is half of that.
Well,
you
said
you asked about 1,000, Toni. Now you're giving us 100.
Well, we had 100 before.
We did.
Caroline.
We had the 100 example. Yeah, I was answering the 1,000 question.
Well, yes, why not? You could do it for no, Caroline. Absolutely right. You can do it for any triangle number now, however big. The point is that if we have any triangle number, it is the position in the sequence is what defines it. So T5 is the 5th in the sequence. T100 is the 100th in the sequence. Tn, now we're creeping into algebra, Tn is the nth in the sequence. T1000 is the 1,000th one.
So it is n times n. I'm excited, Toni, because I'm working it out. I'm loving the fact that I'm actually working it out. Tn equals n times n plus 1.
Isn't that lovely?
And then so Tn equals n times n plus 1 divided by 2. And then you simplify it a little bit.
Yes. So what you can say in words without any algebra is that if you want to find a triangle number, right, you take its place in the line, in the sequence, and that's the number that labels where it is, like T5 is in the 5th place, T100 is in the 100th place. And that place number times one more than that place number,
right,
and then divided by 2 gives you that triangle number.
And you can visualize that using the image above, using that rectangle, that you're only working out how many there are in half of that rectangle. And so it actually really helps you. You can visualize the rectangles, therefore you know it's the length times the width, but you only want half of it. So it's actually, you've got a visual aid for it as well.
Well, you've got a visual aid there, and you've also got a shorthand way of writing it down and summing it up for all possible triangle numbers, not just T5 or T100, but all of them. And what I just said now was doing it in words without algebra. But algebra is just a lovely way of actually summarizing. So to summarize it algebraically, you say that the nth triangle number, Tn, is a half of n times n plus 1, or n times n plus 1 divided by 2. Isn't that nice?
That is lovely.
We don't need the algebra in primary school, but it's what we call in primary school pre-algebra. And yes, this idea is simple enough to do with children in primary school, and then it's a very rich activity for secondary school. Now I have another pattern for you, Caroline. What do you notice about this picture? Okay,
now that's messing with my head, Toni. My eyes are going cross-eyed. You did not prepare me for this. My eyes are going cross-eyed. Hold on. One has got more. One more. That's one's a 2, 4, 6. One's a T6, and the other's a T7.
Caroline, what you said before when you wanted to put the two triangle numbers together was you wanted it somehow.
Oh yes, no, you haven't. They haven't been shifted. But
you're right about it being a T6 and a T7. So what we've got here is two consecutive
together to make a square.
Absolutely, isn't that pretty? Two consecutive triangle numbers. You can picturize it, you can visualize it with that picture, and they make a square. That's what you said.
Two consecutive triangle numbers make a square, but two triangle numbers that are the same. Can you go back? Thank you. If you now look at that one, if they're the same triangle number, they don't make a square at all. You can't make that a square.
They make a rectangle.
They make a rectangle.
And we've just used that. Now we've moved on to something new. And we've said, but if we take not two triangle numbers that are the same, but two that are different, and in this case it's T6 and T7, they make a square, not a rectangle.
And the diagonal of the T7 is actually bisecting the 7 by 7 square.
Yes, isn't that nice? What you immediately spotted when you looked at this was this yellow triangle number is T6 and the blue one is T7. And when you add them up, you get a square. And that square has got how many dots in it? It's 7 times 7, which is 49. Isn't that pretty?
That is very, so T6 plus T7 is 7 times 7. So it's 6 plus 1 times 7. And of course it's 49. That makes a square. Yeah, this is new to me. Sergio, this is, by the way, new to, okay, now he's saying it's all right. Sergio's filling in the thing he didn't say earlier. But this is actually new to me. I don't remember seeing this before, and this is blowing my mind. I'm loving this. I'm wondering how I can do this with balloons.
Well, you see, every time you take two consecutive numbers, there's nothing special about the 6th one and the 7th one. I'm just going to leave this for our audience to play with themselves. But if you look at the list of triangle numbers as we've built it up, we've been talking about it, and you put two consecutive triangle numbers together, I'm going to ask you a question. I want to ask everybody to think about this after this session, or think of it whenever you like, if you want to, and see whether you think it's always true. Because I really believe that we shouldn't be telling them all the answers, Caroline. We should be giving them things to think about.
So is this always true?
Yes. For any two, is it always true that for any two consecutive triangle numbers, and there's infinitely many of them, but if you take any one and the one after it, that they add together to make a square number? Or you can look at it the other way round. You can say, can any square number be split into two triangle numbers?
Can any square number be split into two consecutive triangle numbers? So it's always the connection between the square numbers and the triangle numbers. Okay, that's where I'm going with it. I'll shut up. Oh my goodness, I'm getting excited here, Toni. Is there a connection between square numbers and triangle numbers? Oh my goodness. And go on.
And does this connect with the Gauss's Eureka theorem? Because remember, that theorem which we just talked about when we were thinking about Gauss was that take any number at all. I mean, I don't mean any number, actually. I mean any whole number or counting number.
Yeah.
You can write it as the sum of one triangle number. And well, if it is a triangle number, it's only one, and that's it. If it's a square number, it'll be the sum of two triangle numbers. And, well, will it? That's what we seem to be thinking about with this particular picture. And then if it's not a triangle or a square number, Gauss's Eureka theorem says, well, anyway, you can write it as the sum of three triangle numbers. We haven't proved that. But
do we have to say integers? Is it
positive integers or counting numbers or natural numbers? They're all the same, really. Okay. Now here's a question. Can square numbers also be triangle numbers? Well, the answer is obviously yes. The table shows you that yes, they can, because the number 36 is 6 times 6, which is a square number, and it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, and that's a triangle number.
So does that apply to all square numbers?
No. 49, for example, 49 is the next square number after 36. 49 is 7 times 7, and that's not a triangle number. And you have to go right on through to 1225 before you get another one. And I've left it to our viewers, our other people to find out what that is the square of. But it's the triangle, the 49th triangle number, which is a half 49 times 50. And then the next one after that, you go quite a long way before you get to the next one, which is actually 204 squared. Okay, but there are actually infinitely many of them. It is quite an advanced proof, so we won't go any further with it.
I'm intrigued by the expressions that have been used to describe the triangle numbers on the bottom row. So I should be investigating those and making sure I understand how they work. I also really like the fact that the rows on the triangle are colored in different colors, and then they're represented within the square. So you can really see clearly which of the dots represent which of the lines in the triangle. Really nice.
It is nicely done, isn't it? It comes from Wikipedia, but actually those pictures help with the small numbers, but we wouldn't want to start drawing the pictures for the bigger numbers.
Indeed.
And then to continue with that, it becomes more algebraic. So if we go on from there, we've got another big question. Can we generalize this to 3 dimensions? And the answer is yes, we can. But now, isn't this lovely? These are pyramids, and at the grocer's shop, you'll see a stack of oranges or other fruit like that. They're not spheres, but they're almost spherical. And on the bottom layer, you've got 16, 4 by 4. And then the next layer up has got 9, 3 by 3, and then 2 by 2 with 1 on the top. So you've got a stack there of layers which are actually square numbers. And when you look at the face, you've got the triangle number. Isn't that?
It is.
Isn't that wonderful?
I've seen this done with cans as well. So this is great. Grocers are working with triangle numbers and square numbers, and who knew?
And you get your square-based pyramid,
Yeah.
which is a nice, efficient way to stack cans, as you say, or yes, for a display. Mm-hmm. We talked about the handshakes problem, and this is simply the problem that if you have however many people you've got in the room and everybody must shake hands with everybody else, how many handshakes would that be? Now, with COVID and social distancing, we've replaced the handshake with a bow, the Japanese style bow, where you bow for, not like a performer does on the stage to the whole audience. In this particular case, it's the Japanese greeting where you must greet one-to-one. So it's a one-to-one greeting. So you don't hold hands, but you each bow to each other. So whether it's handshakes or bows, how many would there be? Now, as you see, this is a classroom in Tanzania. I took this picture. I was working with these children, and you see on the board there, it says handshakes, and then it says people, and where it says whatever, handshakes, it's a number of handshakes. So if there's only 2 people in the room, well, that's easy, it's only 1 handshake. And if there's 3 people in the room, the children had just worked out that if there were 3 people and everybody shook hands with everybody else, there would be 3 handshakes.
So it's two people, 1 handshake, 3 people, 3 handshakes. Okay, go ahead, because it's hard to read. I'm just reading it out.
But now these 4 girls at the front are working out, there's 4 of them, and they're working out how many handshakes. And the children in the class are watching and counting as they do the handshake. So everybody's participating, but it's the girls who are actually doing the handshakes. And they're trying to find out how many handshakes that would be. And, well, we talked about this quite a lot a couple of weeks ago. And remember, it could be bows. I was in Bagamoyo. It's a lovely place on the coast of Tanzania, and just across the water from the island of Zanzibar. All very romantic. It's a wonderful place.
It's spectacular, yeah.
It's a wonderful place because, as you see in that classroom, there's a mixture of Christians and Muslims all living very harmoniously together, as they have done for a couple of centuries. And there's a lovely story there, but we told that last time. After they had done that in groups of 4, they all of the children made up groups of 5 and tried it out and worked out how many handshakes for groups of 5 and then 6. And these were the answers that they got. And if you think about what we were doing a few minutes ago, when we're talking about triangle numbers, I'm sure you'll recognize that those are the triangle numbers, 1, 3, 6, 10, 15, 21. But this time we've chosen to do a rather obvious thing, to say, well, we need to really include 1 now, not triangle number 1, but the number of people. So if there's only 1 person in the room, there's nobody else for that person to shake hands with. So now we're starting at the triangle number 0. And that's even more of a special case, Caroline. You see, you thought that 1 was rather a peculiar triangle number. And now, if you see that if you keep going back, so from 21 to 15, you take off 6. And then from 15 to 10, you take off 5. And then from 10 to 6, you take off 4, and then you take off 3, and then you take off 2, and then you take off 1. You go back to 0. So you see, the 0, or as I called it, 0, is in the same pattern, isn't it? So it is a special triangle number. A bit special because you couldn't draw, well, you can imagine no dots or 1 dot and being a sort of shrunken triangle. But there it is. Let's think again about the triangle numbers. Now, Caroline was saying earlier that she wanted to see the triangles look like that, which we'd looked at before, that like the red balls there. But in fact, when we looked at them earlier, they were sort of on their edge. They weren't like these balls. They were, they were drawn a little bit differently. And in fact, these are equilateral triangles, whereas the triangles that we saw earlier were right-angled triangles. But the whole point is they are the same pattern, aren't they?
Okay, so it still works. Okay, go ahead.
So T4 is 1 plus 2 plus 3 plus 4.
Mm-hmm.
And you're being asked here, what is T5? Because there's a question mark there and the picture isn't drawn for you. And well, but all you have to do is to think of the pattern. And it's 1 plus 2 plus 3 plus 4 plus 5. And it's a bigger equilateral triangle that stands a bit higher with a row of 5 along the bottom. In the pattern of red balls, we're starting at 1. In the number of handshakes, we're starting at 0.
Yes, because there's 2 people to make 1 handshake.
Now, when children are learning mathematics, a good teacher will encourage them to spot patterns, because maths is all about patterns. There's so many patterns in mathematics. And to think why those patterns occur, and always to be able to understand and explain why things happen. So we've spotted a pattern for triangle numbers. We spotted that handshakes, the answer to handshakes, seems to be given by triangle numbers. So why? And now we're going to look at why. Because you see, if you look at that picture, and if you think about it, the picture has 2, 4, 6, 8 people standing around a circle. And we did this with string. We talked about doing this with string. It's what you call people maths. So when we talked about this a couple of weeks ago, we talked about 8 people around a circle, and each of them well, passing a ball of string across the circle, not to the next person, well, passing a ball of string across the circle to everybody else. But we did it in a continuous loop, but we won't go back over that because there was a lot in that. In fact, we also did a one on what was it, Caroline? Path to the Stars. So
I'm just looking for that picture because we had a picture from Maca doing exactly that in real life,
yes, exactly.
in that dome. And I'm looking
up
for
at the top.
picture.
Anyway, what you can do is to look at all of these activities: Path to the Stars, Handshakes, and Mystic Roses on the Aiming High website, and you'll see then the connections which we're talking about. We've only got 10 more minutes, so we need to move on. Now, in this picture, what you see is 8 people with all of the chords across the circle, which are lines that go from everybody's hand to the 7 other people. Okay? So what you see from each person there is 7 chords across the circle going to each of the other 7 people. So then 8 people each shake hands with 7 other people. Does that sound familiar? It's actually a picture which illustrates the idea of the handshakes. So in a sense, the maths is the same. It's what we call, well, what I often call being in disguise. You see, the handshakes was this mystic rose in disguise, and they were both triangle numbers in disguise. And there's the correct mathematical term is it's isomorphism, which means things change in the same way. So there's your connection, and isn't that lovely? And so this begins to give you an explanation of why it's triangle numbers. You see, if you think of 8 people, each shaking hands with everybody else, when there are 8 people in the room, each person shakes hands with 7 other people. So why isn't the answer 8 times 7, which is 56?
Why is the answer 8 times 7?
Why is it not 8 times 7?
Or why is it not 8 times 7? If you look at each, 1, 2, 3. Okay, what have we got there? 8. Well, each person, each of the 8 people has 7 chords, 7 diagonals. That's what Sophia meant by the diagonals, 7 chords. But whilst some of them they don't all have 7.
No, they all have 7.
They double up. Yeah, but they double up. So you've already counted 7 with the first person. So the second person along, you only have to count 6 of them. Oh, here we go. There goes the triangle.
No, wait a minute, Caroline.
No, the second person, you're only counting 6 of them.
No, if there's a line that goes from you to me, we're 2 of the 8 people in the room. If there's a line that goes from you to me, and I count that as a handshake between us, but I also have counted the line that goes from me to you. So I've counted every line twice.
Yeah, that's what I was saying. I clearly didn't say it very well.
Oh, you did? No. 8 times 7, and half of that because every line was counted twice. Now, if you look at this summary here, then, if there are 2 people, there's 1 handshake, which is the first triangle number, or we call T1 rather. And if there are 3 people, there are 3 handshakes, which we call the triangle number T2. If there are 4 people, there are 6 handshakes, which is the triangle number T3, and so on. And okay, so with as the pattern goes on, you can see for yourself there on the screen. With 6 people, you've got 1 plus 2 plus 3 plus 4 plus 5 plus 6. Or T15, and that's 15 handshakes, which is T5, and so on. And so that shows you why everything connects with everything else. which is a lovely idea. Now, there's only 8 people around that circle, and it's something that if you're a teacher, you could get your children to do as people maths with a ball of string. And if you wanted to do it on pencil and paper, then it's a very easy diagram to draw. And Caroline remarked when we last talked about this, that smaller children could draw that, and they could then colour in parts of it to show the symmetries and to make it look a pretty pattern.
I'm always looking for ways to include the younger children or the lower attainers, and this is such a great exercise. You start with a circle with only a few dots, or even just 2 dots, and it just gets the insight in how many lines do you need to join 2 dots. Well, it's only 1, even if they're on the circumference of the circle, and then you just add 1 more dot. Now how many lines do you need? Add 1 more dot. So start really simple, and then the child can stretch to the point at which they're then stretching, and then you stop for a moment, another day, and maybe
now, Caroline, I'm
more.
very conscious that we have actually we've taken longer than we had planned to talk about Toni. Some of these things, and we do want to say about women in maths and science, don't we?
Oh, so go ahead. Oh my goodness, Thursday, yes.
So we've only got a short time to do that, and so we need to look again at the triangle numbers for T15 and T16, because you see these 2 mystic roses are slightly different, and it's intriguing that with 16, of course, you've got diameters in, so all the lines go through the center. We saw that last time we talked about it. And with an odd number of people around the edge, if you think of it as people around the edge or points around the edge of the circle, then none of the lines go through the center, and you've got this hole in the middle. But you see from what you that for 15, it's 105 handshakes, and for 16 people, it's 120 handshakes. Now then, what we want to do is to talk for our last 5 minutes about women in maths and science.
I had completely forgotten about this. Go, go, go. Yes. Wow.
So the reason is that the United Nations General Assembly adopted a resolution declaring that 11th of February would be the International Day of Women and Girls in Science. And so we've found this very nice website. Now, Caroline, do I have to stop sharing and share again?
Yes, you have to stop sharing. Well, no, we can see it, but it's quite small.
Oh,
no, I think it might.
No, we'll just talk through. Okay.
Can you press, Toni? Press the green button on top left. The maximum.
Oh, what a good idea,
one.
Caroline. Yes, that's better. Thank you.
That is much better. Yeah.
You can see it now, because you see,
yeah.
I can't see what other people are seeing, but it's on my own screen. Well, I can, but anyway, I wanted reassurance. So sorry about the adverts here, and we will give you the link to this, because we're not going to be able to do justice to this wonderful set of 20 women. Now, Mary Anning was a remarkable lady. This is on the coast of England, around the place called Lyme Regis. It's the Dorset coast, which is often called the Jurassic coast, because she found fossils there of dinosaurs, huge, huge fossils. And the scholars from the universities, well, that was Oxford, I think, university got interested, and they came down to Lyme Regis, and she was quite a simple woman who'd just been collecting seashells to sell in her father's shop when she found these fossils, and then she became actually just as skilled as the highly educated archaeologists. Amazing, isn't it? So,
yes.
Caroline, do you want to talk about Maria Sabella Marion?
So, no.
Well, she was a botanist. Okay, she was a botanist, and she made discoveries like insects hatch from eggs. She was 17th century, so it's a long time ago. So a lot wasn't known then, and she studied insects, and she wrote, and she drew their pictures of them and classified them. Then there's Sylvia Earle. She was a diver, much more recently, in 1935, and she did a lot of research about oceanography. And then this was the first, Mae Jameson, she was the first woman, went up in a space shuttle in the 1990s. Maria Gobert Mayer, she was a theoretical physicist. Now, I can't do justice to this in 5 minutes, but I do recommend you read it for yourself. I want to briefly say about Marion, because she died a couple of years ago, which was absolutely tragic. You see, she was quite young when she died, but already in her lifetime, she'd won a Fields Medal, which is like the Nobel Prize. There isn't a Nobel Prize for mathematics. The equivalent is the Fields Medal. And there's just one more lady I want to mention, because she is so amazing. She's still alive, this lady.
Still alive. She's not just still alive, she's still working.
At the age of 103.
She was born in 1918, over 100 years ago, and she is still working. Now, that's it, my holy grail. She's my inspiration. Still working, still presenting, still out there giving presentations with a microphone at 100.
Well, she's directing some research that other people are doing.
Still presentations at 100.
And Caroline, it's particularly, I really wanted to mention her because it's all research into the human brain and memory and learning. And Caroline does an hour before this hour every week on a Monday, when she talks about the mindset. And the whole idea of the mindset is that the human brain has got some plasticity. It can learn a lot more and do a lot more than people ever believed possible. And this is recent research, really. It's these wonderful discoveries have been made. I mean, she was a groundbreaker in this field, and she's been working in the field for a long time. But a lot of big research was being done in Stanford University in California, and this Brenda, this woman, has been very, very influential, and worked with not just scientists, well, they're all scientists, of course, but doctors who've done surgery on the brain and discovered amazing things. So that's all about the mindset.
We will put that link all over the place.
I just want to say goodbye.
Thank you so much, and we'll see you next week at 5 o'clock UK time for the Happy Maths Hour. For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.